Hi there, my name is Mark Damalira. I am an undergraduate at Texas Southern University. I'm going to be presenting on the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO. We shall talk about what LIGO is, how LIGO works. We shall discuss the differences between LIGO and LISA. We shall talk about the achievements and challenges of LIGO, and then we shall come to the conclusion of the presentation. The Laser Interferometer Gravitational Wave Observatory is a laser interferometer that was designed to detect gravitational waves predicted by Albert Einstein in 1916 in his general theory of relativity. LIGO has two sites, one in Livingston, Louisiana, and the other in Hanford, Washington. What are gravitational waves? Gravitational waves are ripples in spacetime caused by some of the most violent and energetic processes in the universe. Einstein's mathematics showed that massive accelerating objects like neutron stars or black holes orbiting each other would disrupt spacetime in a way that waves of undulating spacetime would propagate away from the source in all directions, much like water in a pond. These cosmic ripples would travel at the speed of light and carry with them information about their origins and clues to the nature of gravity itself. The first direct contact proof of Einstein's prediction of these gravitational waves came only a century later on September 14, 2015, when LIGO physically sensed the undulations in spacetime caused by gravitational waves generated by two colliding black holes 1.3 billion light-years away from the Earth. While the processes that generate gravitational waves can be rather quite violent and destructive, hence massive waves, these waves are extremely smaller, thousands of billions of times smaller, by the time they reach the Earth. In fact, by the time the gravitational waves from LIGO's first detection reached us, the amount of spacetime wobbling they generated was 1,000 times smaller than the nucleus of an atom. The seemingly impossible task to make such small measurements requires equally sensitive apparatus, and this is exactly what LIGO was designed to do. How does LIGO work? LIGO consists of two interferometers, each having two arms, 4 kilometers in length, arranged in an L shape. These two interferometers act as antennae to detect gravitational waves. Interferometers are investigative tools used in many fields of science and engineering, and they work by merging two or more sources of light to create an interference pattern which can be measured and analyzed. The interference patterns generated by interferometers contain information about the object or phenomenon being studied. Interferometers are often used to make very small measurements that are not achievable any other way, and this makes them a suitable and powerful tool for detecting gravitational waves. LIGO's interferometers are designed to measure a distance of 1/10,000th the width of a proton. Interferometers were actually invented in the late 19th century by Albert Michelson. The Michelson interferometer was used in 1887 in the famous Michelson-Morley experiment, which was an experiment with the objective to prove or disprove the existence of the luminiferous ether, a substance that was thought to permeate the universe at the time. All modern interferometers have evolved from this first one, since it demonstrated how the properties of light can be used to make the tiniest of measurements. Later, the invention of lasers has enabled interferometers to make the smallest conceivable measurements, like those required by LIGO. The basic structure of LIGO's interferometers differs little from the interferometer that Michelson designed over 125 years ago, but with some added features. The basic Michelson interferometer consists of a light source, in this case a laser, a beam splitter that splits the laser, two arms with mirrors at the end which reflect back the light from the beam splitter, and then the beam splitter merges the light back and directs it to a photodetector. More about interferometers and the LIGO interferometer. The LIGO interferometers also operate on the principle of interference. When two beams of laser light merge, they generate an interference pattern that depends on how well aligned the light waves are when they combine. When the peaks of the waves of one beam perfectly meet the troughs of another, total destructive interference occurs. And since lasers are used in this case, the result is no light. On the other hand, when the peaks of one beam perfectly meet the peaks of another, total constructive interference occurs, and the result is a light equal to the sum of the intensities of the two separate light beams. There is therefore a possibility of a full range of brightness, from darkness, no light, to the sum of intensities of the interacting beams, which would be total constructive interference. The distance the laser beams travel before merging dictates how well aligned they are when they merge. If the beams travel exactly the same distance, their light waves will be perfectly aligned so that the result is total destructive interference, and LIGO is deliberately designed to have total destructive interference if no gravitational waves are passing. However, if for some reason the lasers don't travel the same distances, their light waves will no longer be in sync as they merge, and this will lead to an interference pattern. The size and added complexity of LIGO's interferometers are far beyond anything the world's first interferometers could have achieved. LIGO's interferometers have arms of an impressive 4 kilometers in length, and this makes them by far the largest ever built. By contrast, the interferometer Michelson and Morley used in their famous experiment had arms about 1.3 meters in length. The scale of LIGO's instruments is crucial to its search for gravitational waves because the longer the arms of an interferometer, the smaller the measurements it can make. And having to measure a change in distance 10,000 times smaller than a proton means that LIGO has to be larger and more sensitive than any interferometer ever before constructed. While 4 kilometers length of arm seems quite huge, if LIGO's interferometers were the basic Michelson interferometers, they would still be too short to enable detection of gravitational waves. And this warranted the modification of the basic Michelson interferometer to be able to detect gravitational waves. This led to the introduction of Fabry-Perot cavities, which includes the addition of a mirror which is placed in each arm near the beam splitter, 4 kilometers from the mirror at the end of that arm. What happens in this Fabry-Perot cavity is that after entering the instrument via the beam splitter, the laser in each arm bounces between its two mirrors about 300 times before being merged with a beam from the other arm. These reflections serve two functions. They build up the laser light within the interferometer, which increases LIGO sensitivity, because the more photons we receive, the more sensitive the apparatus will be. And the second is that it increases the distance traveled by each laser from 4 kilometers to 1200 kilometers, thereby solving our length problem. The light in Michelson's original interferometer only traveled 11 meters of path length. This highly significant increase in the path length of the light in the LIGO interferometers enables them to be sensitive to the order of fractions of the size of a proton, because the 1200 km path length of light amplifies gravitational waves enough that they are detectable and measurable. Just as increasing length increases the interferometer's sensitivity, increasing laser power also enhances the interferometer's performance. Increasing laser power results in increasing the interferometer's resolving power. The more laser photons merge from each arm, the sharper the fringes that are measured by the photodetector, hence a sharper interference pattern. LIGO's lasers first enters the interferometer at about 40 watts, but they need to operate closer to 750 kilowatts if the interferometer has any hope of detecting gravitational waves. However, building a laser with this initial power is a practical impossibility. To overcome this challenge, LIGO uses mirrors called power recycling mirrors, and these power recycling mirrors are placed in the path of the initial incident laser before it reaches the beam splitter. Inside the interferometer, light from the laser passes through the transparent side of a power recycling mirror to the beam splitter and then onto the arms of the interferometer. The beam splitter is a one-way mirror in which half the light passes through and the other half is reflected. The instrument's alignment and mirror coatings and even quantum mechanics ensure that nearly all of the laser light entering the arms follows a path back to the reflective side of the power recycling mirror rather than to the photodetector. As laser power is constantly entering the interferometer, the power recycling mirror continually reflects the laser light that has traveled through the instrument back into the interferometer. This process greatly boosts the power of the laser beam without the need to generate such a powerful laser beam initially. The boost in power generated by power recycling results in a sharpening of the interference fringes that appear when the beams are superimposed, and it is these fringes which will tell scientists if a gravitational wave has passed or not. So how does LIGO differ from LISA? LISA is the Laser Interferometer Space Antenna, and it is a space-based gravitational wave detector constructed of 3 spacecrafts separated by equal distances of millions of kilometers. And LISA is scheduled to launch in the early 2030s. The major differences between LISA and LIGO is that LISA is space-based, while LIGO is Earth-based. The gravitational wave spectrum covers a broad span of frequencies. LISA operates in the low frequency range, which is between 0.1 mHz and 1 Hz, compared to LIGO's frequency of 10 Hz to 1000 Hz. The difference means that the waves LISA is looking for have a much longer wavelength, corresponding to objects in much wider orbits and potentially much heavier than those that LIGO is searching for, opening up the detection realm to a wider range of gravitational wave sources. LISA is also designed to have an even longer arm length, about 1,000,000 miles, which is much longer than LIGO, and this means that it is expected to be even more sensitive than the Earth-based LIGO. From space, LISA can avoid the noise from Earth and access regions of the gravitational wave spectrum that are inaccessible from Earth due to these extremely long arms. The gravitational wave sources that LISA would discover include ultra-compact binaries in our galaxy, supermassive black hole mergers, and extreme mass ratio inspirers, among other exotic possibilities. The achievements of LIGO. One of the major achievements of LIGO was the first detection of a gravitational wave on September 14, 2015. The two interferometers both measured ripples in the fabric of spacetime arriving at the Earth from a cataclysmic event in the distant universe. And this marked the beginning of a new era of gravitational wave astronomy. The possibilities for discovery are as rich and boundless as they have been with light-based astronomy. Some of the other achievements of LIGO include technological advancements or inventions in the fields below: the science of classical and quantum measurements and high-precision metrology at large, optics, quantum mechanics and laser systems, space science and technology, geology and geodesy, which is earth science of accurately measuring and understanding Earth's geometric shape, orientation in space and gravitational field, material science and technology, cryogenics and cryogenic technology, which is the production of and behavior of materials at low temperature, and methods in theoretical physics. Other technological advancements or inventions by LIGO include photothermal interferometer, adaptive laser beam shaping, high-power modulator, interferometric displacement sensor, among others. The challenges of LIGO. LIGO's greatest strength is also its greatest weakness. Because LIGO is designed to be extremely sensitive, it can be disturbed by vibrations from trucks driving on nearby roads, or even from vibrations from earthquakes on the other side of the world. To solve this challenge, sophisticated seismic isolation systems that include active and passive damping systems are employed to counter these sources of noise. To achieve sensitivity such as that of LIGO, the interferometer arms needed to be extremely long. To counter this, Fabry-Perot cavities were installed in the LIGO interferometers to bounce the laser beam back and forth across the 4-kilometer arm length up to 300 times to achieve an effective path length of 1200 kilometers, thus increasing the sensitivity of the interferometers. Lastly, maintaining the stability and purity of the laser light is one of LIGO's biggest challenges. Therefore, the mirrors that LIGO uses are of the highest quality available, both in material and shape. They are made of very pure fused silica glass, and they absorb just 1 in 3 million photons that hit them. This allows for most of the laser light to be reflected. In conclusion, gravitational wave detectors such as LIGO are one of humanity's greatest strides in the field of science. Not only has LIGO benefited astronomy and astrophysics, but other fields of science and technology as well. The remarkable ability to detect gravitational waves is a doorway to a different and deeper understanding of the events in the universe through the detection and study of the weakest of the fundamental forces.